Welcome back, everybody. Um, let's proceed with each day of set until is a unique subgroup of Z of order. Alright. Moreover, these are right. So it's a very uh, kind of idea. There's actually nothing to move it forward. As I said, proof is kind of very much. Um, Note that Zn is cyclic as one bar and inverse are generators Zn, right? Therefore, by fundamental theorem of cyclic group, every subgroup Zn cyclic, in particular, or as rather, let's look at this one in particular as order of one rather is n. Therefore, for every divisor k of n, there exists Zn is n by k of. Let's just if I look at Zn, note note is Zn. Zn is marker here. Zn is nothing but 0 bar, 1 bar, 2 bar, so n minus 1 bar. So so this would be always true for Zn. Take an example quickly to actually point it out, whatever we have just said. Let me look at Z24 with addition modulo 20. So this is cyclic, right? So let's write down Z24 rather. Beg your pardon. What is that? Z24 would be 0 bar, 1 bar, so on up to 23. So let's look at the subgroups of this. Like so, look at what happens to 1 bar. First of all, it starts with identity, right? For every divisor of n. So, what are the divisors of n? So, solution. Let's look at this. So, therefore, note that order of Z24 is equal to 24. And divisors of 24 are what are the divisors? 1, right? Then 2, 3, then 4, then 6, then uh, 8, right? Then 12, hotels, and 24. 1, 2, 3, 4, 5, 6, 7, 8. Right? So I should have 8 subgroups. Let's look at that. First of all, we have identity. That's 24, right? That's precisely 24. 24 is nothing but 0. That is nothing but singleton 0 bar. And what's the order of this? Order is this is fine, right? I look at n by k, get 24 by k here. If I put k equal to 1, I get 20. Then if I put k equal to 2, I get this is bar, 12 bar, right? Would be nothing but 0 bar, it's identity, right? Then 12 bar and 24 bar gives me 0 bar. So this order is. Then we have for 3 here, this would be I forgot. No, this would be 8, right? Put 3 here in place of k, then this would be um 8, right? 8 bar rather. So what would be this? 0 bar, 8 bar, 16 bar, and that's it. The 24 bar will be back to 0. So order is 3 as I said. K equal to 1, this is for k equal to 2, this is for k equal to 3. K equal to 4 would be this. K for k equal to 4, this would be 6 bar. 6 bar would be 0, 6 bar, 12 bar, 18 bar, and back to 24 bar. So the order is k equal to 6. This would be 4 bar, right? This is 0 bar, 4 bar, 8 bar, 12 bar, 16 bar, 20 bar, and back to 24. That's 0. So order of this is 6. Order is 6. Then k equals 8, right? Then 24 by 8 gives me 3 bar, right? What would be this? This would be, right? This would be 0 bar, 3 bar, 6 bar, 9 bar, 12 bar, 15 bar, then 18 bar, then 21 bar, and back to 0. So the order of this order is, right? K equal to 12. This would be exactly 2. This is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and that's it. So the order of this is the moment I take k equal to 24, I get this to be 1, and that's pretty much z, sorry, z. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 subgroups. And also we know the fact that how do we check out if I look at subgroup generated by any other element, you can check out that you can just check out this uh, any subgroup will be equal. This would be kind of 24 identity. But apart from that, if I want to look at the generators, let's look at the generators quickly. What are the generators? This generators, right? Right. Any generator would be of the form a raised to j. Remember, right? So this will be you find one generator, then if a is a generator, right? Then a is same as a raised to j, provided GCD of j and n is 1, right? Remember that. If I look at this, if I look at this here, then uh, generator is 1, right? So j times 1 would be generator of this subgroup, provided GCD of j and 24 is 1, provided GCD of J and 24 is what are the generators? Let's look at quickly. So one is obviously there, right? Then this is one obviously is there. And what are J's with GCD with 24 is 1. 2 is not there, 3 is not there, 4 is not there, 5, right? 5 would also generate the same subgroup. Then 6 is not there, 7 is not 7, yes. 8 is not there, 9 is not there, 10 is not there, 11, right? 12 is not there, 13, right? 14 is not there, 15 is not there, 16 is not there, 17, uh, 18 is not there, 19, 20 is not there, 21 is not there, 22 is also not there, 23, 4, 5, 6. So these are exactly the generators of this. You can just check that 5 of 24 would be nothing but 24. 24 would be 2 squared, 3, sorry, 2 cube 3. So this would be 24, 1 minus half, that's half, into 1 minus 1 by 3. If I look at what is 524 by the formula, this would be 2 by 3. So this comes out to be 2, 2 gets cancelled. And what we have is 8. We'll have exactly 8 generators, and these are the generators of this group. That's how you can see what are the generators of this group, and you can also see what. So these are all the subgroups isomorphic. I mean, sorry, which are just Z24. Then you can do the same thing for this, right? Any other subgroup, you take any other element, it would either generate entire group or subgroup generated by 2, 3, 4, 6, 8, 12, or 20. That's the kind of idea we uh, similar. Let's look at with that kind of thing. Let's quickly look at what are generators of what would be the generators of uh, subgroup, right? Uh, so let's look at this quickly. Uh, Another problem here. Okay, so, so let's look at. So question is as follows. Um, find find all the generators. Find all the generators. The generators. Okay, of a subgroup of order 9 of group Z Z36 edition. So we don't even know. We don't have to find a kind of a specific like this. What all I know is the generator. Since one is a generator, one generates 36, right? Z36 rather, right? Any generator would be of the form J times 1, right? J times 1, where GCD of J and 9. That sorry, I'm looking at. I'm beg your pardon. I beg your pardon. What I'm doing is I'm not finding generator of Z36. I'm finding generators of subgroup order 9. Okay. So if I look at a subgroup of order 9, right, then it's pretty much generated by 36 by uh, I should get the uh, 9 here, right? So what would be this? This 4, right? So this would be 4, right? 4 would generate order of 4 would be 9. So I know that 4 is one of the generators. What are the other generators? Just look at J times 4. Sorry, J times 4, right? J by the fundamental theorem of cyclic groups. Just look at J times 4, where J and the order of 4 is relatively prime. So what are the generators I get? First of all, 1, that is 4 generates, right? Same subgroup as uh, 2 and 9 is also relatively prime. So this is 8. 4 to the 8. Then 3 and 9 are not relatively prime. 5 and 8, 5 and So, as I said, if I look at 4 with 1 with 9 rather, the GCD is 1, then 3, oh, sorry, 2 with 9 also the GCD is 1, 3 is not. 4 with 9 is GCD, I mean GCD is 1, so this will be 16, right? That would be also equal to 5 with 9, that would be 24. I am going model 36. So sorry, 20 rather. That would be same as 6 with 9 is not 1, 7 with 9, yes. So that would be 28, right? And 8 with 9 is also 1, right? So that would be 32, right? And this bar here, so don't forget them, just to imply that they are equivalent classes. So this would be all the subgroups. That this would be all the generators of the subgroup of order 9, right? And we are this would be all the generators of or subgroup of order 9, and we know that since this is cyclic, this subgroup is unique, right? Whatever subgroup we have whatever subgroup we have of order 9, that's the unique subgroup. So one can look at more counter examples, more examples rather, sorry. Um, then uh, let's look at the generators. Find the generators. Find the generators of is equal to this is a subgroup example of order 40 46. Okay. Well, A generates, then by the corollary, right? If A generates, A raised to K will also generate, provided GCD of K and K and 45 is 1, right? So what are the possibilities if I look at uh, well, A would certainly be generator, 2 would be, right? A squared will also generate, A cube won't, A raised to 4 will also generate, A raised to 5 won't, A raised to 6 won't, A raised to 7 also would, A raised to uh, uh, 9 won't, A raised to 10 won't, A raised to 11 would, A raised to 12 won't, 13 yes, right? Right. So we can look at that, you know, uh, and so on. You can continue this, right? So uh, that would be the generators of right. Be plenty more, right? You can find them out, right? How many generators? So if I look at this numbers, tells me that the generators of this group, right, is nothing but yeah. I'll leave it to the remark. Okay. So we have seen that generator has something to do with that number and order of the number and relative order, right? So let's first of all look at a remark. We'll write a remark first. Let me put that in a kind of square shape, kind of take that out whenever needed. Uh, like this. So remark. Okay, what does it say? Once you have generator n by d, the subgroup of order where D is the divisor of n, and G is nothing but generated by A, right, which has order n. All the other generators, right, of A raised to D are of the form A raised to D raised to J, right, where GCD of n and J. That's what we have is the note. Let me this order of UN is nothing but UN is phi of n. Sorry, this I'm in that same zone, so it's n. But everybody must be knowing this by now that order of UN phi of n, and it's a very important function in our let's look at that. So that this right here. Uh, if D is the positive divisor positive divisor of n, then number of order D in the cyclic group of order n is, so if I look, let's look at a cyclic group, then number of elements of order D would be nothing but phi of D. Let's quickly get the proof out. Okay, so since D is the divisor of n, therefore by fundamental theorem of cyclic groups, right, G has a unique, let G be a cyclic group of order n, right? G has a unique subgroup of order. G has a unique subgroup of order D, right? Isn't it? Say A, right? H equal to A, right? Note that order of the subgroup is also equal to D, right? Uh, so let, so this is true, right? So let G be any element. Let G be any element. G be any element of G such that order of G is equal to T. Right? I'm taking another element whose order is also G. This would imply that this is the same order as T, then this would imply that the subgroup generated by order of G would be same as I mean the order of the subgroup generated by this same as uh, right. So this would imply that this are equal because this is a cyclic group. Therefore, what will happen is there would be a unique subgroup, right? Of already, right? This would mean that G must be inside A, right? So and since G was arbitrary element in G of order D, this would imply that all elements of order D belongs to, right? All elements must be there inside A, which has order D, right? Note that further, further, note that all the elements of A are of the form, they have the form A raised to K, right? Where K is between, because this has order D, right? The moment you look at A raised to D, you get identity. So this must be less than or equal to D, right? And and further, let us write down and and A raised to K is same as subgroup generated by A if and only if GCD of K and uh, D rather, sorry, right? D is 1, right? So how many such elements can I find now? Okay, and look at all the elements. First of all the elements must be in D, right? And all the elements must be like all the elements of order D must be there in D, right? And what should happen is the GCD with um, uh, D, all the elements. I mean, how many such elements can I find, right? Uh, if they are of order D, they would generate the same subgroup as A, first of all. And how many such elements can I find? First of all, they must be the any element would be first of all A raised to K, and whose GCD with sorry which lies between 1 and D, right? It can be taking can be K can be taking value 1 to D, and what should happen is K must be relatively prime with D. How many such therefore how many such elements I can find? The number of such elements, the number of such elements, any element of order D must be there in A, right? So if A is my set, any element of order D must be here, but any element here would be of the form A raised to K, right? Such that K is between D and 1, right? And it must be relatively prime too. If this has order D, A raised to K has order D, right? That means it could generate the same subgroup as A. Then what should happen is K and um, D must be relatively prime. So how many such elements can I find? Exactly 5. Point set give. Hence the all right. So let's look at the one final theorem in the topic. What we have is the following. We have already seen what happens in cyclic groups. Let's look at what happens in finite groups. Okay. theorem. In a finite group, G, right, the number of elements of order D is a multiple of proof. Okay. In a cyclic group, what happens is it's exactly equal to phi of t. In a finite group, it would be a multiple of phi of t. Okay. Well, let's prove this quickly. Nothing to nothing much in this. Okay, so let G be a finite group. Okay. So the very first case is suppose G does not have any element. It does not have any element order D. Then the the result is true as phi of D would divide 0, right? In this case, this is true. This is divide. I hope this is clear. Clear. If not, let's kind of write it again. Phi of t would divide 0. Um, so suppose that suppose that uh, there exists A in G, right? Such that order of A is D, right? Then what happens? Then if order of A is D, then we know that the subgroup generated by A will have phi of D elements because it's cyclic, right? Of of order, okay, right? So suppose all the elements of order D are in A, then we are done. That means they will exactly be phi of D elements, right? Suppose there exists B in G such that B does not belong to A and order of B is also D, right? Then subgroup generated by B will also have phi of D elements, right? Isn't it? It also will have, and they don't have common elements, right? And this guy and this guy will not have this any common element. Let's also get that case out. Suppose C belongs to A intersection B such that order of C is also D, right? Since this belongs to this, then what happens is C belongs to A and C also belongs to will also belong to B. This implies subgroup generated by C would be same as subgroup generated by A. If there's a common element, then precisely they are equal. All are all are uh, equal, right? It belongs to, so he from here subgroup generated by C will be equal to A. From here subgroup generated by C will also be equal to B, and you know, so all would be equal, right? Therefore, what happens is this implies B belongs to A. If this and this are equal, this implies B belongs to A, which is a contradiction. Which is a contradiction. Which is a contradiction, as B does not belong. This implies A and B is will not have, right? Write this properly. Therefore, A and B does not have any common element of order, right? Isn't it? Right? Therefore, there are phi of D plus phi of D, so twice phi of D elements in, okay, if these are all the elements of order D, then we are done. Otherwise, continuing as above, continuing as above, we conclude that the elements. So if not, then I will have another element of order D. It will generate a subgroup in such that elements of that will also be. I mean, number of elements in that subgroup will also have exactly phi of D elements, and they both will not have any common elements, right? So it will be three times phi D and so on. We conclude that number of elements, number of elements of order in a finite group is a multiple of. That's the proof we're looking for. All right. Let's end this idea with a kind of remarks. Okay. Remark one. Uh, if I look at pi of any p raised to n, this is nothing but p raised to n minus p raised to n minus 1. P is prime. Okay. And phi is a multiplicative function. This is right for any a comma p for all a comma p. That works. Call this as multiplicative. Okay, you'll see in number theory what is a multiplicative function and completely multiplicative and well that's what we have. Let's end the session or the chapter with a nice kind of an idea. Let's do a lattice, okay, of Z30. So the question is draw the lattice representation of draw 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 the lattice representation of subgroups of Z30. Okay, so let's look at this one. First of all, uh, order of Z30 is 30, right? What are the subgroups? Let's write down. One is a subgroup. For every divisor, I will have exactly one subgroup, right? So one is the one 30 by 30 by 30. right? Then I will have 30 by uh, 2, that is 15, then 30 by 3, that is 10, and 30 by 5, that is 6, then 30 by 6, that is 5. Sorry, this is not equal. Yeah, sorry about that. Then what we have is um, 6, then this is 5. Then what we have is 3, then 2, and then we have Z30. Z30, and this is 0. And these are the all subgroups, right? So let's look at this one. What is this? Subgroup generated by 0 is the singleton 0. Subgroup generated by 15 rather would be 0 and 15, right? The subgroup generated by 10 is nothing but 0, 10, 20, right? The subgroup generated by 6 is nothing but 0, 6, um, 12, 18, 24. Subgroup generated by 5 would be 0, 5, 10, 15, 20, 25. Right? Then subgroup generated by 3 would be bigger: 0, 3, 6, 9, 12, 15, 18, 21, 27, 24, first of all, 27, and that's it. And subgroup generated by 2, right, would be 0, 2, and so on up till 28. And subgroup generated by 1, of course, would be entire Z 30. Right? So if I look at the lattice kind of a representation of this, right, then what happens is Z 30 would sit on top, okay, right? That's subgroup generated by 1. Let's write it properly. This is nothing but subgroup generated by 1. So this is subgroup generated. So let's actually draw this. Can understand the lattice structure. This is 1. Everything is subgroup of this, right? So let's do this. So then what we have is the subgroup of this is here 1, okay, 1 here kind of, you know, and the third one is, if I can, you can nicely see that I'm trying to draw a lattice. I hope I'm successful doing this. Generally, I'm not, because I'm a very bad uh, painter when it comes to painting, but I hope this time I can't draw. I'm a very bad artist. Let's look at this one. I hope I can do this. Let's pull this off, guys. Okay. Man. Okay. So what happens is this is 2 here, right? 2 is direct subgroup of that. Then 3 is a direct subgroup of this. Right. 5 is not coming anywhere in the picture. Right. So 5 is also here. Right. Now what happens is 6 is a subgroup of 2. Like if I look at elements of this and elements of 2, they would be same, right? So let's do this. Okay, shapes. Okay, nice here. Okay, okay. And I have also from here. Then I have also another from here. So as I said, 6 is a subgroup of this, right? Um, 3 will also have 6, right? We'll do that. If you look at 15, 15 has 0 and 15, which are the elements of 3, right? 15 and 0. So 15 is here. A subgroup of 5 is nothing but 10, right? 10 is here, right? And all this comes and meets um, 0, right? So do this. First of all, if I look at this 3, 3 is 6 is a subgroup of 3 also, right? So draw this nicely. You can draw it better than me because then 15 is a subgroup of 5 also, so you can draw that also, a link between them, right? Um, 10 and 3 doesn't have any link, right? 6 and 15, well, 6 and 15 doesn't have a link either, right? So and then this all comes and meets 0. So let's do that. Put it down. Okay. So that I need to just kind of draw this first. Draw a line here and yes, draw a line here between these two. Okay, and a line between these two. We can draw this in a proper way. I just thought of giving a lattice. Oh shucks. Okay. Thought of giving a kind of a lattice diagram. Oh man. Yeah. I hope you all can kind of get a better figure of this. This all comes and meets 0. Right? Nicely. Precision. This is 0. So 4, 4. So this is lattice. So everything goes and kind of on a top kind of a thing. This is a subgroup of this. 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 This is also a subgroup of this. This is also a subgroup of this, and then all are subgroups of the group, right? This is kind of a lattice. It's kind of a lattice. We can kind of make out. 10 is a subgroup of 5. 5 is a subgroup of 1. 6 is a subgroup of 3. Like that, right? It's it's a nice thing. So I can leave an exercise, draw a lattice, okay, for the subgroups of Z, 40. And then you can have a nice figure for yourself and can check out. That ends with the cyclic subgroup. If you have any doubts, you can write it down to me. We would start with computation. Thank you.